In this video, we will be using the data from our last video to create a confidence interval for the difference of proportions. If you remember from the last video, we were given a yawn seed to some subjects and no yawn seed to some other subjects, and we recorded whether or not they yawned after some time sitting in a room. P1 was the proportion who were given the yawn seed, and 29% of them yawned after sitting in the room. P2 is the proportion of people who were given no yawn seed, and 25% of them yawned after sitting in the room. So we're going to use this data to calculate a confidence interval for the difference of proportions. You'll remember from Chapter 8 that the general formula for a confidence interval is given to you on the formula sheet. Statistic plus or minus your critical value times the standard deviation of the statistic. Sometimes that's called standard error. And the reason we call it standard error sometimes instead of standard deviation is because confidence intervals are the only statistical test-like thing that uses the sample data. Because that's all we have. The whole purpose of a confidence interval is to use sample data to make a conclusion about the whole population or to make an estimation about what the whole population does. So now let's talk about what each of these things is for a difference in proportions. So the statistic here, we're trying to find a confidence interval for the difference of proportions. So the statistic is going to be those two proportions subtracted, not P2. P1 minus P hat 2, that's our statistic. We're dealing with proportions, so our critical value is still going to be Z star, and I'll remind you how to get that later on in this video. The standard error is going to be the same standard deviation formula we used in the previous video for sampling distributions. P hat 1, 1 minus P hat 1 over N1, plus P hat 2, 1 minus P hat 2 over N2. The conditions for inference to make a confidence interval are the same, so let's see which ones are not met in this case. The first one is a simple random sample. This was a random sample of people, even though it doesn't say it, and they were also randomly assigned to the group, so that sometimes will meet this randomness factor here. Number 2, you're going to check N1, P hat 1 greater than or equal to 10. In this case, N1 was 34 and P hat 1 was 0.29. That is not greater than or equal to 10. So we can kind of stop there. That condition is not met. So the normal condition is not met. Usually that's the one that's not met. And sometimes what they'll say is, okay, fine, the conditions aren't met, so we will proceed cautiously just because we want to still solve the problem. And what I mean by cautiously proceed is you can still create the confidence interval, but you're going to have some level of doubt in your results just because the inference conditions were not met. You can't be sure about making a normal calculation. And the normal calculation matters for confidence intervals because that lets us use a normal distribution to get Z star. So you need normal to properly use Z star. Now we're just making a lot of assumptions since that condition is not met. So let's calculate and interpret a 95% confidence interval for the data we have above. First thing we need to do is state all of our given information. So state, we're given P hat 1 equals 0.29. P hat 2 is 0.25. So P hat 1 minus P hat 2 is 0.29 minus 0.25, which is 0.04. You can memorize your Z star to be 1.96. If you don't remember 1.96, you can always use inverse normal to get it. So if you have 95% in the middle, then you've got 0.025 and 0.025 on each side. And you can do inverse normal to get the 1.96 if you forget. So 0.025 0, 1, that comes out to 1.96. And you can do that with any percentage in the middle there to get z star. Next, we're going to calculate our standard deviation, or our standard error. So that's going to be p hat 1, 1 minus p hat 1 over n1 plus p hat 2, 1 minus p hat 2 over n2. So if we plug that in, we get 0.29 times 0.71 over 34 plus 0.25 times 0.75 over 16. That equals 0.13. So now we can write our formula, p hat 1 minus p hat 2 plus or minus z star, and then I'm just going to leave that as square root because I don't want to write all that again. So we've got 0.04 plus or minus 1.96 times 0.13. So we need to write that in an interval form. So you'll do 0.04 minus all that and 0.04 plus all that. And you get negative 0.2148 is the left boundary and 0.2948 as the right boundary. It's okay for the proportion or the interval to have a negative value because that means that P2 is bigger than P1. That's all that means. So now we can interpret it. We are 95% confident, always start with that the true, or the population value, the true difference in proportion, and you can always find this in the paragraph if you aren't sure the wording to use right here. True difference in proportion of people who will yawn. You can basically just, this part right here, you can just rewrite in your conclusion. So I just paused and wrote the whole thing out. We are 95% confident that the true difference in proportion of people who yawn given a yawn seed versus not given a yawn seed is between negative 0.2148 and 0.2948. So that means the entire proportion has some negative and some positive. So that means that we aren't actually sure which one's going to be higher consistently because some values in our interval are negative, which means P2 is greater than P1, and some values in our confidence interval were positive, which means P1 was bigger than P2. So we can't be confident that one is higher than the other because some parts in our interval are negative and some parts are positive. So based on our confidence interval, is there convincing evidence that yawning is contagious? So remember, yawning is contagious. That would mean that if you had the yawn seed, you're more likely to yawn. So that would imply P1 greater than P2. Since 0 is inside our interval, that implies that there is no difference because if P1 equals P2, then P1 minus P2 will equal 0. Since 0 is inside our interval, there is not convincing evidence that there is a difference in proportion. So we do not have convincing evidence that yawning is contagious. So let's formalize some of these rules. We have just done a 2-sample z interval. We called it a z interval because it was proportions, and we have 2 samples. So in Chapter 8, we were doing a 1 proportion or a 1-sample z interval. Now we're doing a 2-sample z interval. And our general formula is p hat 1 minus p hat 2 plus or minus z star times the standard error. P hat 1, 1 minus p hat 1 over n1 plus p hat 2, 1 minus p hat 2 over n2. That was our confidence interval, with the conditions that it's both random samples. You also have that n1 p hat 1 greater than or equal to 10, n1 1 minus p hat 1 greater than or equal to 10, n2 p hat 2 greater than or equal to 10, n2 1 minus p hat 2 greater than or equal to 10. That's the normal condition. and our independent condition. Both N1 and N2 are less than or equal to 10% of the population in context. Then you've got your interpreting part, and we kind of talked about this at the end of the last problem we did. But if your entire interval is positive, then P1 is greater than P2. So it's positive everywhere, which means P1 minus P2 is greater than 0. So there's evidence that P1 is bigger, and you would just interpret that in the context of the problem. If you have an entirely negative interval, that means that P1 is less than P2. So if you were to do P1 minus P2, you'd get a negative number everywhere. And so you would interpret that the way you need to. So there's evidence that P1 or P2 is bigger. And you would just interpret that how you need to in the interval. And then in the context of the problem. And then you have negative, positive. If you have negative and positive, that contains 0. So you would either say inconclusive, or you could also argue there's evidence that there is no difference. So you could go any way with that if you have negative and positive. So those are the 3 different types of intervals you get, and that's just kind of a breakdown of what they mean. So now we're going to do a state plan do conclude problem with constructing and interpreting a confidence interval for a difference of proportions. So in this example, I'm just going to highlight some important things as we read it. A research center poll asks an independent random sample of working women and men. So it looks like we're going to have a sample of women and a sample of men here. How much they value job security. So there were 806 women, and 709 of them said job security was important. And then we've got 802 men of the 944 men surveyed said that it's extremely important. So we're going to create a 95% confidence interval for the difference in proportion. And it's important to look here, the difference in proportion of all working women and men who consider job security very important. So that what I highlighted in red is what you'll use when you interpret the confidence interval. It's helpful to use the same wording. So let's define our variables. P1 is going to be the proportion of women who value job security. And P2 will be the proportion of men who value job security. Our confidence level is 95%, and we have our first sample was 806, and our p-1 is 709 out of 806, which is 0.88. Our second sample was 944, and p-2 is 802 out of 944, which is 0.85. So we have 2 different samples, and we're creating an interval of proportions. So that is a 2-sample Z interval. And so once you write that, it helps if you go ahead and write what the formula is going to be. You know you're going to have p-1 minus p-2 plus or minus your Z star p-1, 1 minus p-1 over n1 plus p-2, 1 minus p-2 over n2. You know you're going to use that for your confidence interval. But before we do that, let's plan. This was state over here. We're going to do our conditions. It did say that they were both random samples. So we have a random sample of men and women. The second condition is the normal condition that allows us to calculate a Z star and be confident that it's a normal calculation. So we've got N1 times p-1, and we've got N1 times 1 minus p-1. Both of those are greater than or equal to 10. And then we've got 944 times p hat 2 and 944 times 1 minus p hat 2 greater than or equal to 10. Both of those are greater than or equal to 10. And so now our normal condition is met. And the third one, 806 and 944 are both less than or equal to 10% of the populations of men and women. So there's our conditions. All our conditions are met. That's the independent condition. So now we can plug in numbers into our confidence interval formula. So p hat 1 minus p hat 2 is 0.88 minus 0.85 plus or minus. The z star for 95% is 1.96. Then we've got 0.88 times 0.12 over 806 plus 0.85, 0.15 over 944. And it probably would be helpful if you typed in the square root in your calculator first, so you don't have to type it a bunch of times when you calculate your interval. You can use the alpha y equals feature on your calculator to type fractions. That might make your life a little bit easier doing the math. So when you calculate all that, you end up with negative 0.0019 to 0.0621. So notice already that you have a negative left interval and a positive right endpoint, so there's probably no difference between men and women's views on job security. So let's interpret that. Here's the conclude. We just did the do part of a state plan do conclude. So you want to use the same wording from the original question. So if I scroll a little bit, the difference in proportion of all working women and men who consider job security very or extremely important, that was the same wording as the question. So we're going to say we're 95% confident that the true difference in proportions of working women and men who consider job security very or extremely important is between negative 0.0019 and 0.0621. So there it is, worked out for you to copy down in your notes if you missed it in class. So it doesn't ask a follow-up question about this, but it could say, like, is there convincing evidence that women value it more than men? And in this case you would say no, because 0 is within our interval, so we don't have confidence or we don't have convincing evidence that women prefer or value job security over men. And that would be a state plan do conclude problem that would get you full credit.